Hello, in our lesson today, let us discuss Rutherford scattering. First, let us review the equation of hyperbola in polar form. So this is the equation of hyperbola in polar form. Here we have r and theta. That means if you have a point P on the hyperbola, then that point will be described in polar coordinates in terms of r and theta. And r and theta will satisfy this equation. And d is a parameter defined by the fact that x equal to plus minus d is the equation of the directrix. When r approaches infinity, 1 plus minus epsilon cos theta approaches 0. So from that we can determine epsilon, which is eccentricity, which is epsilon equal to 1 upon cos phi. This phi is the angle theta when r approaches infinity. In other words, when r approaches infinity, theta approaches phi. And another important result is that for a conic section to become a hyperbola, value of eccentricity has to be larger than 1. Next, we have our all important figure here. Red line is the path of the alpha particle and it is approaching a nucleus which is placed at the focus F. M and N are two asymptotes. M coincides with the path of the alpha particle when the alpha particle is approaching the nucleus and the alpha particle is at large distance from the nucleus. And N asymptotes approaches with the coincides with the path of the alpha particle when the alpha particle is receding to infinity. After the scattering is over, the alpha particle is receding to infinity again, and then the path of the alpha particle coincides with the asymptote n. And theta is the angle between these two asymptotes, and we define theta as the scattering angle. Phi is the angle between the asymptote and the symmetry axis, and epsilon is given in terms of this angle phi, which is epsilon equal to 1 by cos phi. Okay, so if this is phi, this angle is also phi. That means we can relate b, which is the impact parameter, in terms of OF and sin phi, because sin phi is b by OF. An impact parameter is defined as the perpendicular distance from the nucleus, that is from the focus to the asymptote m. So now we have defined b and we have defined theta, which is the scattering angle, and also we have defined the eccentricity in terms of cos phi, 1 by cos phi. Now let us define the closest approach, q. Closest approach is fa dash, and you can break it into OF plus OA dash, and OA dash equal to OF dash multiplied by cos phi. That is, then we can sum it, OF plus OA dash equal to OF multiplied by 1 plus cos phi. So that is a relation that we will use in the derivation of Rutherford scattering formula. So one relation is that q equal to OF multiplied by 1 plus cos phi. The second relation is b by OF equal to sin phi, and third relation is eccentricity is equal to 1 upon cos phi, and the fourth relation is theta plus 2 phi equal to pi, or theta by 2 plus phi equal to pi by 2, or phi equal to pi by 2 minus theta by 2. So these are the relations that we will use. So first the epsilon in terms of cos phi, then the scattering angle in terms of phi, then the closest approach in terms of OF and cos phi, and then the impact parameter in terms of OF and sin phi. So these are the relations that we will use from this picture, and we will also use the two equations, one for the conservation of energy and the second for the conservation of angular momentum. So before that, let us define pictorially what is the impact parameter. This is the path of the alpha particle. So when this is the path, we can extend the path here and drop a perpendicular from the nucleus to the path. So that distance, perpendicular distance, is the impact parameter. When the impact parameter is large, the scattering angle is small. When the impact parameter is small, the scattering angle is large. So Wikipedia says the impact parameter is defined as the perpendicular distance between the path of the projectile and the center of a potential field created by an object that the projectile is approaching. It is often referred to in nuclear physics and in classical mechanics. Next we have 4 equations. Conservation of energy. So initially all the energy of the alpha particle is kinetic, so that is half mv square, and when the particle has approached the closest point of closest approach, then the energy is partly kinetic, partly potential. So kinetic energy is half mv m square, that is the velocity at the point of closest approach, and this is the distance of the closest approach, and this is the Coulomb potential. So Coulomb potential is used for the repulsion between the alpha particle and the nucleus. This is Coulomb scattering. Also Rutherford scattering is also called the Coulomb scattering. And this Z prime is 2 for alpha particle, but at the moment let us keep Z prime as Z prime, and at the end we will substitute Z prime equal to 2. The second equation is the conservation of angular momentum. So mv is the momentum, b is the impact parameter, and when the alpha particle has reached the point of closest approach, then this is the momentum mvm, and multiply by the distance of closest approach. So that is the angular momentum at the point of the closest approach. So these two angular momentum must be equal, because the alpha particle is conserving angular momentum as it is passing through the hyperbolic orbit. So this gives the relation Vm by V, and also from equation 1 we get the relation between Vm square by V square. So there is a possibility of eliminating these velocities, and the property of hyperbola that we have already discussed, or if we substitute wave, then V by sine phi multiplied by 1 plus cos phi. So using these relations, we will manipulate and express the relation in terms of the variables which are measured experimentally. So that is important. We have to express the relation in terms of the measurable variables. So first of all, then let us find this ratio Vm square by V square. So 1 minus ZZ prime is square by 2 pi epsilon naught mv square q, and from angular momentum we get v by q equal to Vm by V, second relation, and v by q is again coming from the property of hyperbola, b by q equal to sine phi by 1 plus cos phi from equation 4. Sine square phi is 1 minus cos square phi, that means 1 plus cos phi into 1 minus cos phi. So 1 plus cos phi is cancelled from numerator and denominator. Then we get 1 minus cos phi by 1 plus cos phi. So that means we get equation 7. Then let us substitute the value of q here in terms of b. Then we get 1 minus zz prime is square by 2 pi epsilon naught mv square multiplied by sine phi by b into 1 plus cos phi. That is 1 by q is substituted in terms of 1 by b. Right hand side is 1 minus cos phi by 1 plus cos phi. Now let us multiply both sides with 1 plus cos phi. Then this 1 plus cos phi goes, this 1 plus cos phi goes, and here we have a 1 plus cos phi. This one cancels with this one. This cos phi comes to the other side, becomes minus 2 cos phi. And this minus goes. That means we have plus, right hand side plus 2 cos phi. So that is what we have got. The next equation, zz prime e square by 2 pi epsilon naught mv square b sin phi equal to 2 cos phi. Now we can express it in terms of tan phi. So we can express in terms of tan phi b equal to 1 by 4 pi epsilon naught zz prime e square by mv square tan phi. Now we can express phi in terms of theta. Then phi equal to pi by 2 minus theta by 2. Then tan phi becomes cot theta by 2. Then we get b equal to 1 by 4 pi epsilon naught zz prime e square by mv square cot theta by 2. So this is the relation between impact parameter and the angle of scattering. That is when a single nucleus is approaching a single alpha particle is approaching a single nucleus. Then the impact parameter and the angle of scattering has this relation. But in a realistic experiment, there is no single alpha particle. We have a beam because we have a radioactive sample, and from there we can collimate a beam. And also there is no single target nucleus. We have a foil, a gold foil or a silver foil. So for a realistic experiment, we have to do some appropriate modifications to this equation. This is the relation between b and theta. So we confine ourselves to a single scattering nucleus, but let us consider a alpha particle beam. So then alpha particles approaching it, that single nucleus, along different asymptotic paths will have different impact parameters. So to begin with, we consider a single nucleus and a alpha particle beam, and later on we will include many nuclei. That means the target will contain many nuclei. So in this beam, alpha particles approaching it along different asymptotic paths will have different impact parameters. So let us consider a ring. This ring, the area of this ring is 2 pi b dB, and so the number of alpha particles crossing this ring will be 2 pi b dB multiplied by n, where n is the number of incident particles per unit area. Expression has b and dB, and we can re-express b and dB in terms of theta, because we have a relation between b and cot theta. So let us substitute b and let us substitute dB. So we take dB d theta, which will also bring in a minus sign here. So but both of them will have this constant factor, 1 by 4 pi epsilon naught zz prime square by mv square. So we will substitute b and dB from this equation 9. So we substitute, then we get dn equal to minus pi n, then 1 by 4 pi epsilon naught zz prime square by mv square whole square, and then this cosec square theta by 2 becomes cosec cube theta by 2, and because we had a cot, so we have a cos theta by 2, and this minus sign has come from the derivative. Now let us put the value of z prime equal to 2, then we get a 4 here. So minus 4 pi n, this factor square cosec cube theta by 2 cos theta by 2 d theta. This is dn, that is the number of alpha particles which has scattered between the angle theta and theta plus d theta. Area of ring can be found by cutting the ring. We can cut this ring with a pair of scissors, and then this is r, and the circumference is 2 pi r sin theta, that is the length of a rectangle, and the width of the rectangle is r d theta. Then the area is r d theta multiplied by 2 pi r sin theta, which is 2 pi r square sin theta d theta. That is the area of this ring, so we call it ds. Then the solid angle which is subtended by this area, subtended by the ring at the position of the nucleus, is given by ds by r square. So that means ds by r square is 2 pi sin theta d theta. Then we can express sin theta in terms of theta by 2. Then we get 4 pi sin theta by 2 cos theta by 2 d theta. That is ds by r square. So thus we can calculate the number of scattered alpha particles in angle theta to theta plus d theta per unit solid angle. All of them has gone through theta plus d theta, but we have to calculate per unit solid angle. because this ring has subtended the solid angle of d omega. That means we have to divide by d omega. dn we have got already, and then we have to divide by d omega. If we divide, then we get dn d omega equal to n multiplied by 1 by 4 pi epsilon naught z square by mv square whole square cosec 4 theta by 2, because in d omega we also had a cos theta by 2, so that has got cancelled with this cos theta by 2, and this cosec cube was there, that has become cosec 4 theta by 2. That is dn d omega. Now only one alpha particle per unit area. This is not realistic, but we are just doing it in a hypothetical way, because after all we have to do it in the method of unitary methods, in the way the unitary method of arithmetic, where now we put n equal to 1. So then dn d omega is written as d sigma d omega. D sigma d omega is the expression for dn d omega when n equal to 1. That means we get 1 by 4 pi epsilon naught z square by mv square whole square cosec 4 theta by 2, and this d sigma d omega is called the Rutherford scattering cross section. This gives the relation between the differential scattering cross section and the angle theta. This is called the differential scattering cross section. So here one single alpha particle is scattered through the angle theta and d theta. So it provides the probability of scattering that single particle by a single nucleus between the angles theta and d theta, and also per unit solid angle. So that is called the differential scattering cross section. So this is differential scattering cross section. Now we will use this is one nucleus and one alpha particle, but in the experiment we have a different situation, because we have a foil target which has many nuclei. So now let us generalize our result to the case of a realistic case. Before that, why d sigma d omega is named cross section? Because z square by r has the dimension of energy. That means z square has the dimension of energy multiplied by length, and mv square has the dimension of energy. That means energy gets cancelled, we get the length square, because this is dimensionless. That means d sigma d omega has the dimension of area. That is why it is called cross section. The probability of scattering is known as the differential cross section. Now let us examine the dimensions. We have got the dimensions already. This is the origin of the name cross section. Now in a realistic situation, if the target, there is a target sheet, and the target sheet has the number density, that means n nuclei per unit volume, this target sheet. But remember that we are considering a unit cross section. That means for us, for that unit cross section, the volume is t. T is the thickness. You may think that how come a thickness become a volume? It is possible when you are considering the unit cross section. That means multiply the number density with t, then you will get the number of nuclei contained in this volume. So that those are the nuclei which will act as scatterer for that single alpha particle. So that is the concept of density of packing. So if density of packing is high, then the alpha particle will face many nuclei, scatterers, and if it is low, then it will face less number of scatterers, scattering nuclei. So in the capital N, the number of alpha particles are incident on a sheet per unit time, whereas delta n of them are scattered into solid angle capital delta omega. Then delta n is proportional to both n and delta omega, both. And in addition, delta n is also proportional to the density of packing n1, which is n into t. That means delta n is proportional to capital N, then n into t, then capital omega, d omega. That is the differential solid angle. So this is a proportionality, and the proportionality constant is the differential scattering cross section. That is how we have defined the differential scattering cross section. So then we can write an inequality instead of writing a proportionality. Now we can write an equality. So delta n is d sigma d omega n n t capital delta omega. Now let us substitute the value of d sigma d omega. Then we get n n t, then this factor square cosec square theta by 2 cosec 4 theta by 2 d omega. Now this d omega is can be written as ds by r square. Then we can substitute here ds by r square. Then we get write ds by r square. Then we can write delta n delta s, and we get a 1 upon r square here, because then this r square will come here and ds will go there. So we can write delta n by delta s. So the number of scattered particles at scattering angle theta which passes through the solid angle d omega per unit area. So before that, let us calculate this strip, area of this strip. So let's draw the area of a strip intercepted by two cones of half angle theta and theta plus d theta on a sphere. So area of this strip is also the area subtended by d omega at the center. Two cones, so one cone is half angle theta, another cone half angle theta plus d theta. So the first cone has intercepts a ring R1, and second cone intercepts a ring R2, and the area of the strip intercepted by these two cones of half angle theta plus d theta on the sphere is the shaded region, and this area is the ds, that is ds by r square is d omega. So we have divided by ds delta s. So delta n delta s is this. So this is the relation which is experimentally measurable. Ns equal to delta n by delta s, and this was verified by Geiger and Marsden in 1913, and they verified the dependence on scattering angle, which is cosec 4 theta by 2 law. They verified the dependence on thickness of target, which is proportional to t, and also they verified the kinetic energy alpha particle, that is E half mv square, because you have mv square whole square in the denominator, then you have ns proportional to 1 by e square. So all three of them were verified by Geiger and Marsden, but Geiger and Marsden could not verify the fourth relation, ns proportional to z square, because they didn't have that much accuracy in their experiment. But later it was verified by James Chadwick in 1920, and James Chadwick also is the discoverer of neutron, but this is one of his earlier works in 1920. So in his work, what he did is that using the Rutherford scattering, he verified the relation that nuclear charge is equal to atomic number. That means using the Rutherford scattering formula, he arrived at a relation which is true, and he did it for a number of nuclei. So in that way, Chadwick verified this relation ns is proportional to z square. That means all four of these relations are now verified, and the Rutherford scattering formula is very well established. So the distance of closest approach now we can calculate for suppose a specific value of the energy of alpha particle 5.486 MeV. We get Qm equal to 2.47 multiplied by 10 to the power minus 14 meter for silver target, and Qm equal to 4.15 multiplied by 10 to the power minus 14 meter for gold target. And since nuclear radii are smaller than these estimates, because this is estimated from scattering by Coulomb repulsion, so the actual radius will be even smaller. So since the nuclear radii are smaller than these estimates, it's obvious that the nuclear radii should be 10 to the power minus 4 to minus 5 times smaller than the atomic radii. So this is the really the physics that was extracted from Rutherford scattering. A nucleus contains a very small volume within the atom. So probably this is one of the most important results even in the history of science, that for the first time we could understand that the atom is mostly empty space and nucleus is at a very tiny place, very tiny volume is occupied by the nucleus. Also, Rutherford's model has a serious drawback. The serious drawback is that the electrons are moving in circular orbits, and when it is moving in circular orbits, then it is changing its velocity, the direction of its velocity, and when it is changing the direction, it is also has acceleration, and any electrically charged particle, when it has acceleration, it emits electromagnetic radiation and it will lose energy, and finally the electrons will ultimately plunge into the nucleus. So that means the Rutherford's atomic model is a unstable model. So this drawback was corrected by Niels Bohr's atomic model in 1913, and afterwards Bohr's theory in a more developed form produced quantum mechanics, which formed the theoretical basis of all subatomic phenomena. Now here we have some references. Ernest Rutherford, Scattering of Alpha and Beta Particles by Matter and the Structure of the Atom, Philosophical Magazine, Volume 21, page number 669 to 688, year 1911. Geiger and Marsden, The Laws of Deflection of Alpha Particles Through Large Angles, Philosophical Magazine, Volume 25, page 604 to 623, year 1913. And this is Rutherford, Nuclear Constitution of Atoms, published in Nature. This is a talk given in the Royal Society, volume 105, page 500 to 501, 1920. And here Rutherford mentioned discovery by Chadwick that the dependence on Z square, the Z square dependence was announced in this talk in 1920. K.S. Crane, Introductory Nuclear Physics, this is a classic book. Wheely, 2008, and Kaplan's book on nuclear physics, published previously it was published by Addison Wesley, now it is published by Narosa, published 2002. So this will give you a lot of material to read on the alpha particle scattering and Rutherford's formula, and which is very important because even today the advanced experiments in the very advanced labs, they use this idea of scattering cross section and impact parameter and this density of packing and so on. But even though they have very large computer codes, but inside those codes, if you look through that codes, then you will see that there is scattering cross section, then there is impact parameter, and then there is density of packing. So these concepts are still in use even today. So I hope that you have enjoyed this talk on Rutherford scattering, and thank you for watching.